Who's on First is a 1930s comedy sketch made famous by the duo Abbott and Costello. The comedy routine gets its humor by using uncommon surnames for baseball players on the team, such as who, what, and why. Costello becomes increasingly confused and frustrated with Abbott's explanation, leaving the audience in stitches while witnessing this great example of miscommunication. This sketch shows that a misunderstanding can be comical, but this isn't always the case. A lack of understanding or miscommunication can and most often produces negative results. Achieving engineering efficiency and, of course, understanding how modern building automation strategies work and operate is the goal of engineers and operators alike. For example, a strategy involving equipment rotation is quite common throughout the built environment. However, the understanding and practical implementation is often still misunderstood. Understanding the basic core concepts and how to implement this strategy in Control Basic is going to avoid the frustration and confusion that can occur during some of these implementations. Specifying and deploying an appropriate equipment rotation strategy depends on a variety of factors. For example, a strategy based solely on equipment runtime will ensure that, of course, all components age equally. Conversely, an approach that rotates on a specific time or date ensures that operators will likely be available and can accurately estimate when the actual switchover occurs. Both of these strategies provide effective methods for equipment rotation and, of course, can be combined to create even a third strategy that builds on the strengths of both. Creating a solid, well-understood equipment rotation strategy is going to be the first step in increasing engineering efficiency for implementing really advanced control strategies. With all this in mind, in equipment rotation with a prescribed order and time, we can use that as a foundation on which to build. Now, regardless of the strategy used, all strategies are going to require the same fundamental information. The most essential information needed is the number of devices we need to rotate. And this can be achieved by the following program example, like local variable A stores the number of devices to be rotated. Something like A equals 4, just asks how many devices. To add the strength and the benefit of knowing who is turning on and when, the day and time needs to be determined. Knowing the who and when can serve building operators with a routine-based schedule during their normal working hours to prevent switching or possible failures that would occur during non-working hours. We can use other local variables like B and C to hold this information, something like this. B equals Tuesday, what day is it to switch? C equals 8 o'clock or 8 a.m., what time is it to switch? And once these items are known, it's now time to determine the who's going to be the lead, or in other words, which piece of equipment is actually currently running. So to control multiple pieces of equipment properly, it's going to be advantageous to number the equipment accordingly. Ask ourselves who's on first, who's on second, third, fourth, so on. This lead integer value can then be used in the equipment programming for each device. It can also be assumed that any integer higher than the number of actual devices controlling the system is going to impact the strategy negatively. We want to add a safeguard here to limit this number to the appropriate range of devices, and we can achieve that with something like lead equals limit the lead between 1 and A. The next step is to prevent the strategy from rotating more than once a week. A simple code example can test if the day of the week, DOW, is greater than the switch day, which is Tuesday. If this is true, we could add another local variable to be used as a flag to prevent the lead integer from indexing just more than once a week. We can achieve this with something like here. If day of the week is greater than B, then just stop D. And if the lead has already rotated this week, then the strategy has already done its job. If the rotation flag is true though, the program can just simply end with something like this. If D, then end. It's now time to determine if the present day of the week is not the actual day configured to allow the equipment to rotate. So a piece of code like this could ask the question, if the day of the week is not equal to B, then just simply end. It's asking, is it Tuesday? And if it isn't Tuesday, as in that example, the program can simply just end. In the same way, it's now time to determine if the present time is not the time configured to allow the equipment to rotate. Something like the code here can ask the same question. If the time is less than C, then end. That's asking, is it time to switch? And if it isn't 8 a.m., as we put in our example, of course we can end the program here. As the strategy progresses line by line, and if the program hasn't ended yet, it can just be determined now that it must be the appropriate day and time to rotate the lead. So the code here can advance the lead integer by 1, just simply lead equals lead plus 1. To ensure that the lead integer just doesn't keep counting past the number of devices, the lead will need to be indexed back to a value of 1 to start the entire process over again. So something like if lead is greater than 4, then just lead is going to equal 1. Once this strategy is complete, the rotation flag will just need to be set to prevent any additional rotation throughout the week. So simply put, start D. Well understood and of course implemented strategy for equipment rotation will increase engineering efficiency by just providing a solid communication foundation for collaboration between engineers and programmers. In addition, knowing the answers to the who, when, and how of a control strategy will avoid confusion and of course frustration and provide a solution that is no laughing matter.